Hi everyone. Welcome back to the class 103. So last class we talked about um, the minerals and also plate tectonics. So we I think I changed the sequence. I think after we talked about minerals in chapter 2. In chapter 3, mineral and rocks, and I think it's time we can talk about environmental issues about minerals and rocks. So I think this is like logically continuous. So I'm going to do that. And after that, we're going to learn ecology and geology, and then we're going to talk about some kind of ecology and geology. And then in the second part of the class, which is the after midterm exam, we're going to come back to talk about the natural hazards and all the earthquake in part 2. Okay, so, all right. So in this chapter, because our modern society, basically, we strongly depends on the availability of mineral resources. And as we learned from the class, as the population increases, even though the rate is getting slower, but as the population increases, and we will demand more and more resources, especially when people's living standard want to, match up with each other. Then we are, going to have uh, uh, ever increasing resource crisis. And so some people think that we're going to reach the capacity of the earth to absorb all those environmental degradations as well associated with using those resources. So in this chapter, we're going to try to understand the relationship between human population and resource utilization. Going to try to understand why minerals are so important to our modern society, understand the difference between a resource and reserve and why that difference is important, and know some of the factors that control the availability of mineral resources, understand the environmental impact of mineral development, know the potential benefits that biotechnology can offer to environmental cleanup associated with mineral extraction and production, understand the economic and environmental role of recycling mineral resources, and understand the relationship between sustainability and use. So first, let's look at a case. When you look at the picture, which also the cover picture of this chapter, this is the Fossil Trace Golf Club, which used to be a mine, an open pit quarry for about 100 years. So in this quarry, there are carbonates, and between the carbonates layers, there are clay. Basically, those are the erosion old soil and for a long time. And it's between beds of carbonate. And these layers of clay between the limestone beds, people use them, mine them, and it's a very high quality and use them to make bricks or construction materials. And then it's a huge open quarry. Now these days, it's being reclaimed. So all those clays being used to build buildings, including the Colorado Governor's Mansion is built by the clay mined from this pit. And you see there are sort of continuing construction here. So today, and this being reclaimed and built this golf club. And it looks beautiful. There's grass on the top, and also there's a wall of carbonate. And in this carbonate, very interesting, there are actually has dinosaur fossils and also has plant fossils and so forth. So it's become to be actually attraction, local attraction for tourists. People came to play golf and watch the fossils, and these are the the carbonate wall. You can see all those fossils drive by. So very interesting place. So this is one of the successful reclamation and changing the mine, which later we'll see that has all kinds of issues, into some kind of environmentally friendly and then beneficial to society. Okay, so mineral is very important, and we use mineral all the time. And that's the sort of backbone of modern society. And we basically strongly depend on the availability of mineral resources. And for example, the living standard, the standard of living increase with the increased availability of minerals in useful forms. Society have succeeded in locating, extracting, importing mineral resources and have been very prosperous. And availability of mineral resource basically has been used as a measure of the wealth of the society. And the United States is a developed country, has very rich. One of the token or is that they use huge proportion, it's unproportionately high amount of resources compared to its population. Okay. So in other words, the population resources per capita is very high. The mineral resources is very important in people's daily life and also as overall economy. For example, the processed material from minerals accounting for 5% of U.S. GDP. Okay. And this is here in the textbook. There's an example. Seeing that if you go to the office, okay, almost everything is some kind of, you need some kind of mineral resources. For example, computer, it's probably contains lots of different kind of element metals like nickel, gold, silica, aluminum, zinc, iron, and also I said petroleum products. So just be careful. So you can see that this is a little bit different from what I talked in last chapter. And I said that minerals, geologically speaking, mineral is inorganic solid. And you can see that the petroleum or coal or natural gas, based on that definition, is not other non-minerals. But here in this book, they call them minerals. And I would say that they're resources. I mean, strictly speaking, they're not minerals, but they're resources. So you can ignore those petroleum products here. But basically, there are metals, most of the computers made of all has to come from somewhere, extractions of mineral resources. That's true, except those plastics which is petroleum products. Pencil, these are pencil. In the old days, it's called lead pencil. It's actually in the center. It's not lead. It used to be lead, which is not healthy. So actually, these days it's all graphite. It has graphite and what is not a mineral, and then because it's organic material, and then clays. Telephone has copper wire, gold. The plastics and the books have limestone and clay. So you probably wondered why books has limestone, clay. Those are just to improve the finish. So most of the book, those are just like fibers. They compress and then they solidify. And in order to have certain kind of gloss or finish, nice finish, then people put additive to it. Since some knowingly things like clay and limestone, which has very different finish, and paper looks very solid and much nicer. So those books contains some limestone clays. Pens have, sometimes want to have clay, silica, and talc. BlackBerry, basically all the electronics contains all kinds of metals. And people said that your iPhone contain like 40, 50 elements. Camera, same thing. Chair has aluminum and also sometimes iron to make it more solid. Television, stereo, these are all electronics. They have a lot of different things. The wall, most of the wall are made of drywall. Drywall, basically, it's gypsum. Also the coating, sometimes titanium oxide, make it white, and also some colors. The chest, metal chest, they're basically iron, nickel, and so forth. And sometimes the ram is made of brass, copper, copper and zinc, or brass rim. So you can see that it's all of them, okay, are coming from some kind of mineral resources. So minerals, people use mineral resources every day, everywhere. Okay, but most of the mineral resources are non-renewable. What that means? It means that even though we mine those from the ground, most of those are kind of mineral resources take millions of years to make. So it's not or geological times, maybe it's fine. Geological timescales after a few million years, then it's probably you can make new ones. But in our time, these are basically non-renewable. It's too long for humans' life. Okay, so next question, we want to differentiate two terms when we talk about minerals. Normally, we talk about mineral resources and mineral reserves. Okay. Mineral resources, in the textbook, there are two definitions. One is that elements, compound minerals, or rocks concentrating a form that can be extracted to obtain a usable commodity. Okay, it's a little bit subtle here. It said usable commodity. Okay, sometimes this is a little vague. A little bit more pragmatic way to describe this is that a concentrated naturally occurring mineral materials includes solid, liquid, gas in and or on the crust of Earth in a form that can now be potentially extracted at a profit. Okay. So instead of saying usable commodity, we said extract at a profit. This actually makes some differences. Some commodity is not necessary to be profitable. So we prefer the second definition. But there are something sort of useless now these days, like in and all the Earth, crust of the Earth. Maybe in the future there's spatial exploration, and there's could be resources from other planet. So you can remove that, just to concentrate naturally occurring material, solid, liquid, and gas, and then can potentially be extracted at a profit. Okay, so why we mentioned that it has to be extracted at profit? You see that. There's in economic geology, we always using a term is called concentration factors. Concentration factor means that a natural concentration of all those metals or element is actually very low in the crust. In order for that to be mineable, explorable, and it has to reach a certain concentration. And then in typical ore, they're much higher than in the crust. And only when they reach to a certain percentage, it's profitable. Otherwise, the much money we earn by mining them, extract them, are lower than how much we're gonna pay to do that. So from that, you know that this is depending on economic conditions, the price of those ore, the element example, and then are also some kind of legal factors, whether how much pollution it can make and how much we could spend to get rid of or prevent those pollution to come from. So the ore has to be a certain grade. So here, the concentration factor, for example, for gold in nature, this is all percentage. This is This is 4 ppb parts per billion in the rocks. Normally, in rocks contains 4 ppb of gold. In order for that to be mineable, you have to reach about 10 ppm, which has the concentrate factor. Basically, you use this percentage divided by that is 2,500 times. So for any gold, in order to be mineable or profitable, you have to concentrate the form. You have to mine the concentrate form. The concentrate form has to be like 2,500 more abundant than in the natural silicate rocks in the crust. So for mercury, it's even more. It's 10,500. And for lead, it's 2,500. And of course, this also depends on the economy, right? So if the gold price keep rising and rising 10 times, maybe 1 ppm is mined. So this is sort of the idea. So based on this conversion factor, that's basically that's controls how profitable they are. Aluminum is a little low. If it's 4 times, we can mine it because aluminum is more abundant in the crust. About 8%. If you reach about 35%, that's turned by. Reserve is defined as a proportion of the resource that's identified and currently available to be legally extracted at profit. So resource and reserves are different. And in the textbook, they made a analogy saying that reserve is like all the cash you have in the bank, and you can use it anytime you want. Okay. Whereas resources means that the potential commodity you have, including your house, your future income, and so forth, and those things are not usable now. So we call that resources. Maybe in the future, you can use it, or maybe you sell your house, you can use those as cash. So that's the difference. So in this figure actually is explained much better. So for any kind of mineral or materials, and some of the resources being identified, and some of it's not and discovered. Okay, so it's been identified and it's economic, means we can use them, we can explore them. We call that reserves. If it's marginally economic, we call that marginal reserves. If sub-economic, which is not the concentrate factor is too low, then we'll say that's sub-economic resources. It's not reserves because it's not usable, not at profit. Whereas if it's undiscovered, and if we know it's there, then it could be hypothetical resources. If in some places we never know, and we speculate they could be there, we call that speculative resources. So that's the direction of increasing degree of geological assurance. So this is the difference between resources. Resources are something that's profitable, but it's not sort of either because it's not known, or it's undiscovered, or predicted, or it's sub-economical values, then we call that resources. Whereas something you know we can use them, we call that reserves. Okay. All right. So how many type of mineral resources? So there are the following, not limit to these. I'll give you some examples. The first one is the element for metal production and technology, and these are can be classified according to their abundance. For example, these are including like iron, aluminum, chrome, manganese, titanium, magnesium, and so forth. Iron and aluminum is probably the most, account for about 3% of all minerals mined in the US. Then there's scarce metals like copper, lead, zinc, tin, gold, silver, platinum, uranium, mercury, aluminum, and so forth. Those are also mined. Those are elements for metal productions and technology. The second one is building materials. Building materials are those gravel, sand, crushed stone for concrete, These are actually, although metal is very important, but it turned out that these materials, and also including volcanic ash, they are account for about 94% of all minerals mined in the United States. By the way, I'm using the fifth edition of the textbook, and it was written in 2012. So some of the data are a little obsolete, and the one I mentioned that those are based on 2009 data. These days, there are better. Probably the number will change, but the idea is the same. Building material is always the number one resources. Again, the mineral resources are necessary. Some of them are just, like crushed stone for concrete. Those are rocks, but those are not minerals. And for minerals, there's like it contains both minerals. Sometimes has organic matters. Sometimes are actually supposed to say they're rock resources, not saying mineral resources. Rock resources including organic and inorganic materials. And also, it said the minerals for the chemical industry, and in the textbook, both basically said those are petroleum products like oil, petroleum, crude oil, and they make plastics. And those are actually not minerals, okay? So these are actually like coal, they're rocks. They are resources for chemistry industry, but not necessarily mineral resources. Just keep in mind. Real mineral resources for chemical industry, including things like the noble metal, and then they are doing as catalyzers, and then very important chemical industry. Mineral for agricultural, like a fertilizer, like a phosphor and potassium, they all have a nitrate. They're all kind of natural minerals. And also there are synthesized fertilizer as well. Those are not minerals. So we're talking about the minerals for agriculture, which means that those that are made naturally. Just pay attention to it. And some others minerals, including things like precious metal, precious gemstones, like cosmetics and food, and so we use them. Gemstone like diamond, sapphire, ruby, those are precious gemstones, and we sell for profit. Last one is energy mineral resources. These are, some of them are not really minerals. Okay, so you should say energy resources, not rather than mineral resources. And like coal, they're basically rocks. So oil and the gas are not really energy. But the energy mineral resource, you can think like uranium oxide, uranium compounds, thorium. They are the materials, resources for using in the nuclear power plant. Those are energy resources. So currently, the biggest problem facing the mineral resource problem are the following. The first one, we already mentioned that it's a non-renewable resources compared to how much time it's been produced in nature, and the humans, lifetime is short compared to that. There's a finite amount of mineral resources. So thinking about if I'm teaching another class, which is the ES 106, if you take that class or in the future, you will see that Earth itself, you can consider that's a closed system, which means that there's a very limited amount of things going out, a limited amount of things coming in. So therefore, so this resources we have, it's whatever on Earth. And so the amount of mineral resources is finite. It's not endless. And because it's non-renewable, so we can, if one place use more, then the other place will have less. And because of the growing population, we have growing demands of the resources. And also, because of industrialization and more developed countries consuming disproportionately high share of mineral resources. And then there are also supply shortages. There are, of course, there are economics and capitalism help to resolve this issue. But essentially, whatever country are rich, they will use disproportionately high share of mineral resources. Then another one is that the distribution of mineral resources are depending not on the population. It depends on the geology. And later we'll see that it basically determined by the plate tectonics. So if it's determined by plate tectonics, then it doesn't matter population are distributed. So you can see that this help people, this make force people to trade them. Then once it's trade on the global market, then the wealth of the country becomes to be a very important factor rather than population. And technology is also very important. Okay, so how people respond? What are the ways? How can we respond to this limited availability? So there are a rule of thumb, have few choices, like we can find more resources. Of course, it's always we can turn those resources into reserves. For example, we find most abundant ones, and then we can improve our technologies, or we use less or make more efficient use of what is available, which means that we can improve our extraction technology so we can extract more. So same as find more resources, more sources. Or we can find a substitute. So we can find a replacement. If one thing is being used up, then we can use something else. Recycle, always. For some metals, once it's been used, and you can always melt it and then reuse them. And for metals, it's quite easy thing. So do recycle. See that will reduce the environmental impact later when we talk about environmental impact. And last one is that can we find a way to still operate and then without using them? For example, people talking about the green buildings these days, sometimes they don't use some material like steel, try to reduce the amount of them and only use the natural material like wood, something that's more renewable material. Okay, so for this chapter, for mineral resources, there are basically two sided problems. One is geology problem. So geology determines where minerals are going to be found, or minerals can be found, or those elements can be enriched, okay, and how we make ore. The second one is socioeconomic component, which are the environmental impact and the regulations. So first, we're going to talk about the geological part of mineral resources. And so there are a few terms. Number one is the definition of ore. Ore means useful metallic minerals that can be mined for profit. Basically, in other words, we showed this table before. Basically, you have to reach a certain concentration factors. If the concentration factor is high, then that means it's profitable. Then we call that as ore. And mining potential, depending on many things: technology, economics, politics, with emphasis on profitability and technology feasibility and demands. So these are all very, very important factors. For example, some countries, making some having some more mineral resources, and then they can sell them in the global market. And then for political reasons, they stopped selling them to the global market, and other countries has to find other means to mine them to get those elements. Then the price will be high, and then even though it might not be profitable, but for strategic purpose, some countries still has to develop ways to do that. And we mentioned this. It's basically its concentrating factor. It's the concentration necessary for profitable mining. Gold is about 5,000. If we have a percent in ore only 2,500, then not enough. Of course, this is depending on the price of the gold. And if we doubled, then this concentration percentage ore used to be like sub-economic can be economic. So this said that's depending on technology, economics, and politics, and how we can make it profitable and feasible. Okay, and also these concentration factor vary, evolve with time. As I mentioned that if in the future there's not enough gold, then the price increases, then these concentration factor are gonna decrease. Some ore could be just sub-economic, could be become to be economic. So also, if we develop better ways to mine, to extract some of the elements from these ores, then we can reduce the price to mine them, then therefore make it more profitable. Then this concentration factor could change. Okay, so how the mineral resources is produced? There are different ways. There are similar to the rocks. They're associated with igneous rocks, including things like disseminated, crystal settling, late magmatic, pegmatic, hydrothermal, and so forth. So then there are metamorphic, and there are continental metamorphosis and regional metamorphosis. Some barrier metamorphosis also produced, later we'll explain, but compared to these are not a lot. There's sedimentary rocks. They have evaporite, placer deposit, glacial deposit, and deep ocean deposit as well. And biologically, they have like phosphor for making fertilizers, and then they have weathering processes can produce ore deposits. These are the ways how to concentrate element or materials in Earth's crust. So here are some kind of distribution, and later I'll show you that lots of these bigger mines, major deposits somewhere, is all close to things like subduction zone and processes and collision zones. So here, and also mid-ocean ridges has lots of them. The arcs has lots of them, and then an interior, there are small deposits that can occur. So later when we talk about the plate tectonics, the effect of tectonics on these occurrence of mineral resources, we're going to come back to this. All right. So first one is genesis of mineral resource by igneous processes. Most ore deposits actually caused by igneous processes. And they can concentrate things like copper, nickel, and gold, even though they were maybe not directly coming from the igneous processes, but originally they came from igneous resources. So igneous resources, basically igneous processes is to melt rocks. Okay, so then they have solid part and the liquid part. Most of the useful element like copper, nickel, gold, they're incompatible. Incompatible means they want to be in a liquid. So this kind of melting process basically is the way, once you turn it to melt or magma, then they concentrate those elements. And then they solidify, then they are, these processes can make sizable, huge amount of copper and zinc and gold, increase their concentration by a lot. Okay, so they also other kind. Basically, the first one is in the textbook mentioned about kimberlite pipes. So kimberlite is kind of rocks. They're Their mafic rocks contains things like olivine, pyroxene, garnet sometimes, and they originated very, very deep part of the earth. They're in the mantle. So those are all the mantle, the lithosphere mantle, if you will. So therefore, the majority composition is actually olivine. Okay, so they are below the crust, and where the temperature pressure is very high. When the temperature pressure is very high, and if you have carbon in it, then you can make diamond. So kimberlite pipes basically is a place that people making diamond. So this is the um, diamond, of course, I learned before, is composed of pure carbon and form very high temperature pressure. Normally, the depth has to be higher than 190 degree kilometer. Then you have melting of the mantle rock come up, and then those diamond being picked up by the melt, and then they come up and they find this like a volcanic neck. Okay, so and then it's like a pipe shaped, and they would call it kimberlite pipe. Kimberlites originally comes from the name from South Africa, Kimberley, and then meaning all this rock assemblage coming from there, then you have this kind of kimberlite pipes. And normally they have they have kimberlite shears. You can think these are ultramafic rocks. These are magma, thinking about the magma, but very basic. Then they crystallize, solidify. Then they have very massive kimberlite neck here. And inside you can find diamond. Okay. And because diamond is very expensive, of course. Diamond is hardest material in the world, in the universe, actually. And then they have very good properties. People want to keep it as gemstone, gateway rings, and so forth. So here is how they mine them. They're actually not mining the surface. Normally, surface is like a lake, big lake. They accumulate water there, and then they have broken ore here, and then they dig a big hole on the side. These days they mine here. Then once they mine this place, they're gonna have to collapse. They have a big hole here. So here is a big picture. Is in the old days people just mine surface. Now these days you have a big mine shaft, and then coming to the bottom where the massive kimberlite pipes. Then you sort of making several drills horizontally, and then you look at each part, and then you collect those rocks and crush them on site, and then using the bin or whatever, and transport to surface, and then you dump the waste and select the diamond. Normally, you crush the rocks very fine grains, then same times use the UV light, and then the diamond has fluorescence, and you can actually see them very clearly, very easily go through the assembly lines. So people make diamond. So this is the one of the biggest hole, human-made hole, dug by hand, and in the world. And then this reason is that people make diamond or try to look for diamond. Okay, so the second way you can find mineral or discover mineral is something we call crystal settling. Crystal settling is in the magma chamber. So in any kind of, especially basaltic lava, before the eruption, they actually gathered or stored in magma chamber at the core of the volcano, and then in those places you actually precipitates some iron minerals, and iron minerals normally have high density like chromite or magnetite. When they form, they are denser than the magma, so they're going to settle down. They are going to precipitate, in other words. So then you have layers of chromite. So and very enriched in chrome and iron. So people mine these to get chromite. These are another sort of processes. It's called crystal settling. This process you can find other kind of So another process is called lake magnetic processes and hydrothermal replacement. Lake magnetic processes including things like pegmatite, which if you go to granite formation at later stage, when the most magma precipitate, then they actually have quite some water. So water is interesting. Water has solubility, right? Water solid is because it's dipole molecules. They can extract. They can combine with metal ions and pull them into aqueous solution. And this solubility increases with temperature. And then when the temperature is very high, then solubility is high. And when they reach supercritical point, supercritical water actually has very, very high dissolution capability. You can dissolve lots of material. Okay, even though normally some material like in the rock is hard to be dissolved, but in the supercritical solution, you can do that. So pegmatic means that you have big grains. At the end stage of magnetic processes, you have liquid and then aqueous liquid and dissolved in some kind of rare metals in it. And then when they crystallize, they form very big crystals because you have space, and then you have huge concentration of some element, then you form from some kind of. So pegmatite is where a lot of people find gems, like in mineral classes or in the gem store, you see geoid, it's a concentric silicon on a lot of times quartz. And then inside is the empty cavity, and inside there's gem quality crystals formed inside. So those are the lake magnetic processes. And also there are hydrothermal replacement. So when those high temperature fluid dissolve minerals, and then they can redeposit in the cavities, in the cracks of the rocks. And then they form cavity filling deposits. Sometimes those fluid can interact or react with some minerals and completely change the minerals. And they have something we call the deposit, replacement deposits. So the picture shown here is actually a panoramic view of Chuquicamata, a copper mine at about 9,000 feet above the sea level. And this is in north of Chile. Okay, so we want a picture show that in Chile, in Andes, there's a lot of mines, and most of the due to the subduction. So this is an open pit, and you can see that it's a huge area, and they have copper, and also has they mostly copper mine. And this is a little truck here as a reference, very, very small truck compared to a huge mine. Okay, and so this is how this is made. This is a good example. They have several processes to have. The first one is related to igneous rocks, which is the subduction zone. During subduction, there's melt, come up, and then during the melting, this like zinc, those are incompatible. They want to be in the melt. They concentrate in the melt, and then they form igneous rocks. Then in these places, there are lots of fractures because there's active subduction going on. So you have faults everywhere, and those faults of some kind of feature zone, and you have precipitation. Those Andes orographic factor always have the moisture coming from Pacific Ocean and start to precipitate rain down. And then they will go through the falls. They're going through the volcanic rocks and start to leach, okay, and start to leach these metals. And then because at the bottom is still hot, okay, so all the like meteor water, whatever, going down there, they'll be heat up. Once they heat up, they're gonna come back, and they leached these metals. Then when they come up, they will deposit because the cracks presence of cracks, they deposit somewhere else, like this. And then they can form a huge copper mine. And this concentration of copper is pretty high, very good ore. And then after that, they start to process them. Okay, so you see that the color of these a little bluish. Okay, so contains the copper. These are hydrothermal processes. Okay, the second kind of process is called metamorphic processes, and metamorphic processes is, similar to igneous processes. Sometimes actually overlapping with hydrothermal processes because they could produce the hydrothermal process as well. So most important processes are contact metamorphism or original metamorphism. Contact metamorphism is the following: is that you have igneous rocks, which is like magma, you rise up. Then around the magma, the temperature is very high. Okay, so then when they see like shale or sandstone or special limestone, then they are going to start to react with them. And the limestone has calcium, and igneous intrusions have silica. Then when they see each other, they make peroxides and all kinds of things. And normally you form a zones, a different zone depending on temperature. It's actually zoned by temperature. So you have different minerals. You have garnet, pyroxene, and different places, and then you form this kind of contact metamorphism, original metamorphism as well. So when you have a big mountain building, you generate pressure and temperature. Some of the rocks will start to be metamorphosed, and during this time, their fluid movement then concentrate the ore or concentrate some element. In this process, it's also hydrothermal processing. It's to say that you can develop cracks, and because temperature here is high, shale contains water, and then when they heat up, the water will move up and they produce hydrothermal fluid, and then they will start to dissolve and transport those elements into lower places and forming ore deposits or forming veins and so forth. You see that depends on what kind of rocks. The thickness of those this contact zones are different. If we go closer to shale, sandstone does not have much to offer, so the deposits zone is actually very narrow. Whereas going to shale or limestone, this zone is much bigger because these host rocks actually gave some element to this igneous body, so therefore to the magma, so therefore they can produce very rich ore. Okay. So if you learned metamorphic processes, you will see that there are actually three metamorphic processes. One is barrier metamorphosis, which means that you can sediments you bury through the diagenesis. If you have more rocks piled up, and you form sediment rocks, and then that if that's basically it's a barrier metamorphosis. If you compress a little higher, pressure thicker crust, then temperature will be higher, automatically higher because of geothermal gradient, and therefore it will enrich some of the element. But that process is, relatively, it's not a high grade because temperature and pressure is relatively compared to contact original metamorphosis is lower. Therefore, the rate is slow. But sometimes, for example, you can find pyrites in the sediments, and sometimes you can be enriched. The reason is not because of temperature pressure; is actually depends on oxygen fugacity. So originally in the ocean, we have a lot of sulfate, and when the sulfate becomes to be reduced, we can combine that's easily combined with element to form sulfate. So the pyrites, chalcopyrites, you can form in the barrier metamorphosis, but not a lot, small quantity compared to contact metamorphosis and regional metamorphosis. If you do have a chance to go to Vermont, Rondax, and you see that there basically it's the contact metamorphism. They make a skarn, which is the igneous intrusion into limestone. They make beautiful pyroxene, beautiful garnet, and also some other not only mineral resources but also some element. So you can go to that Adirondacks Park, and sometimes they sell you a bag of rocks inside. You can outside is actually carbonate mostly. Inside you have rocks and minerals and very gem quality. It's very beautiful. But outside you don't know what's inside. You just spend like $25, buy a little bag, and go back to process yourself. Sometimes you'll be surprised. Sometimes depend on your luck, I guess. Sometimes you're not lucky, you don't find anything. It's probably pretty crappy minerals. All right. So next process to make minerals is the sedimentary processes. Sedimentary processes are actually one of the important processes to make minerals. It's actually not making minerals, more like a sorting, concentrating, enrichment of those minerals. So there's a few things. Like number one is sand and gravels. Sand and gravels can be transported and sorted by wind and water, or river channels sometimes being accumulated by glacial deposits. And these are very good. They're very good building material, construction materials. For sand or gravel, in order to reach them, only thing I guess you need is the sand contains a lot of time has soil or very fine particles between them. So in order to concentrate that, the only thing you have to do is just remove those fine particles. Why you have to do that is because when you try to make cement, concrete, and you only need the sand, and you want cement as to glue them together. Okay, you don't want the small particles. Small particles actually can, like a dirt or very or soil or clay, they can reduce the I would say the strength of the concrete. So pretty much in order to have sand, you only have to wash those things away. So a lot of time, poor quality of sand, gravel, and move here. The first thing you do is actually to wash them, and then make sure all the fine particles gone. Then they mix with big pebbles and also concrete and concrete. The cement. Cement will be cementing all those things together, and then they have a desired effect. So people always want to find them in like a desert or in the river channels, the sandbars, and so forth. So you can find all sorts of sand. And by ocean, same thing. The beach sand, they can use that as the construction material. Only thing you have to remove sometimes carbonate there, and then so in aqueous conditions, actually much better because you don't have to remove those carbonate layers. The only thing is the fine clay, that become to be deposits. Next thing, very important thing, we call that placer deposits. Placer means that you place that there. So these are normally like gold. So what happened is that some of the native element, gold, silver, native means that you can find them in their metal form. Okay, and then or they're just element form. Actually, see not metal form because you can have graphite, which native graphite, native sulfur. You can find them in the element form. In other words. Gold is special. Gold is compared to water, it's heavier. It's higher density, right? So and rocks, a lot of times rocks can contain them, especially igneous rocks will have them. And when they weather, they will be transported by a river, and then they will move, right? So when they move, because the gold's heavier than other things, so they're gonna fall down. When they fall, and if you have a flat surfaces, then all the material at the bottom can be transported and being kicked around. Okay. But if you have a cracks, like here, and all this gold will fall into the cracks and cannot be moved anymore. Okay. So we call that placer deposits. And this is basically the idea. You have some riffles or basically contains gravels and sand. You move down through the river and transported by them. If they're heavy, they're easily falling in the cracks. And the ones that fall in cracks, very hard to get out. And then they will concentrate here. It becomes something we call that placer deposits. And gold is this. Actually, people mine gold using this way. So you have a machine. Then at the bottom, you have a lot of grooves. And then you want the sediments, and you pick up from the river, and you go through that machine. After cycle a few times, and you see that at the bottom of the groove, you find gold. So this is called placer deposits. Another one is something we call evaporite deposits. Evaporite deposits can be divided into three kinds. One is marine, and which is the marine deposits. Marine deposits like it used to be ocean, then uplifting, and sea level goes down, then they will become to be lagoon and being sort of left behind in the continent on the continents, and then because evaporation they dry, and then when they dry, they form marine deposits. Most of them are like potassium and sodium salts. And if you look at for geochemists, we study the fluid inclusions in those like halides. You see that their composition almost same, very similar to the ocean seawater. So you know those are from ocean, even though currently they're on land. They were because of the sea level drops. And then you have calcium carbonate, gypsum, and hydride. For non-marine ones, normally it's a lake or a river, or turn to lake. And then when they dried, this case, it's the Death Valley, used to be a lake. And then you have a lot of evaporation, and all those and sodium, calcium carbonate, sulfate, borate, nitrate, iodine, strontium compound. All those sodium, calcium are originally coming from the weathering of the rocks on continents. And then they accumulate here, and with time, when when this uplifting and when the climate condition changed, and then you have more evaporation than the input, then the lake will dry up. And at the bottom, you find those deposits. And the third one is called brine. Brine is basically, it's not a solid yet. Brine basically is solid water. Okay, so sometimes it's basically coming from the ocean, and then when they dried up, not completely dried up, and then they buried in this kind of buried in the sand formation, and they find this kind of brine liquids. You find these things like thermal springs, wells, salt lakes, and they provide things like bromine, iodine, calcium chloride, and magnesium, so forth. One of the biggest, like lithium, or now we need a lot of lithium because of the lithium battery. They exactly come from this lake deposits. So the lithium is easy to be soluble, and it can easily dissolve in streams and water. Then they concentrate, and once being evaporated, and you can harvest the lithium salt. So here is a map. And all these are evaporites and halides and gypsum and hydride deposits. Those are basically marine deposits, like we focus on Louisiana, Kansas, even in Montana. We have those potassium minerals and halide, gypsum. So those are used to be ocean seawater. And now they crystallize, and they're very, very thick. There's even things places like Michigan, Pennsylvania, they have those. And then for gypsum and hydride, these are used to be like river non-marine. These are also marine products, okay, because in the ocean they have sulfide, sulfide. So it's marine deposits also. Okay. Another interesting thing is something called salt dome. So these doesn't matter what's marine and non-marine, especially marine deposits. They have lots of salt, and then they buried in a formation. Then because of geothermal gradient, the salt can be sort of melted or being heated up. When they do that, they will be expanded. Like then when they expanding, they intruding other rocks and have interactions like salt. We call that salt dome. And these are very interesting. They will form evaporite belts and they can pressed by overlying rocks. And then they will intrude overlying rocks. And in the Gulf of Mexico, Gulf Coast, and these are very good source for near pure salt because during the heating, they basically going through the smelting process. They concentrate in some places and recrystallize. So then they form pure salts. And these are also very important for reserves. For example, here, they're cutting through oil reserves and see that this places, they seal off the oil. And these places, the oil sand, all the oil can come to this place and concentrate in the low banks here. So that's very good. Have oil reserves in those places normally. These salt domes also very important for later when we talk about the radioactive material energy. Then we'll see that one good place to store radioactive material waste these days is put into the salt domes, because when you put them there, they actually keep evolving. And you put on the top, after some time, they're going to be in the middle of the salt dome. They'll be sort of been sealed for at least 1,000 years. So until these radioactive elements decay to have no radioactivity. So this is sort of salt domes. It can be used as resources, also can be a storage site. So here's a table of evaporite and brine resources in the United States in years of supply at current rates of domestic consumption. So basically what means that we have this reserve or reserves, and divide by the annual consumptions. Okay, so it's identified resources, in other words, is reserves. And then for potassium compound, we can use for 100 years. For salt, more than 1,000 years. For gypsum and hydride, we can use more than 500 years. Sodium carbonate, more than 600 years. Borate, 300 years. Strontium, 500 years. Nitrate is unlimited. So in the United States, we have very resourceful, have lots of evaporite. So to at least a few hundred years is not a problem. Okay. And if we consider undiscovered resources, hypothetical and speculative resources, it's even more. Okay. So this is sort of the idea of these things. We have lots of reserves. Okay, next way to make mineral resources are biological processes. Biological processes are basically, first thing is the carbonate in shells. So carbonate is very useful. People make like limestone, let's see, metamorphose. We have contact metamorphose and turn to marble. Then we can put the construction material, make construction material like the countertops, so forth. Also, carbonate can be, poor quality carbonate can be used as to making cement. Ironically, you have to burn the CO2 out, take the CO2 out and make a cement. The picture here is something we call the bone valley. So we know that most of the bones, like fish bone, human's bone, they're made of phosphate. And all over the years, they are mineralized, turn into something called apatite. So this picture shows something called a place has very rich phosphate mines in the world. It's one of the most richest phosphate mine in the world. It's called Bone Valley. It's about 40 kilometers east of Tampa, Florida. This is marine sedimentary rocks composed in part of fossils of marine animals, their teeth, their bones, which who live there, the animals, the organisms, marine animals living there for 10 million or 15 million years ago. So they were used to be the shallow bottom of the sea levels, the shallow sea. So the bottom of the sea, when those marine animals die, they fill up in those area, in this area, and then their bone and teeth, they all aggregated and mineralized, turn into apatite. And so as much as 1/3 of the world's phosphate production coming from this place. So it's a huge amount of phosphate. And we know that plants need nitrogen and phosphate and potassium. Those are the 3 most important nutrients for plants. Okay, next category is making mineral resource by weathering processes. So weathering process, intensive weathering of rocks or soil can produce residual deposits. There are 2 kinds of deposit. One's called residual ore deposits, the secondary enrichment. Okay, so residual deposits, this is a very good example. So this is igneous rocks. When igneous rocks extensively weathered, then things like potassium, sodium, calcium, they are gone. They're dissolved. And then when they dissolve, those iron go into streams, eventually ends up in lakes, could be later become to be evaporites, or in the ocean. Okay, so but the some of the elements not easily to get dissolved, like aluminum, like silicon. In this case, aluminum even more. Sometimes people like gallium also will be concentrated and being left behind because they don't like to be dissolved. Okay. And then they can become to be insoluble ore deposits. And this is apparent igneous rocks. And then they form something called bauxite. Bauxite is aluminum hydroxide, and then or sometimes iron oxide. And then they are forming, once it's forming iron oxide, and then they are hard to get dissolved, the oxic conditions. So they will form this bauxite, and then people use them to mine aluminum and iron sometimes. So this is typical residual ore deposit. All other elements, silica, sodium, potassium, calcium, they can all be dissolved. Only thing left behind are things that are not dissolvable. Okay. Same as this. This is the another kind of thing, which is called secondary enrichment during the hydrothermal processes that we mentioned before. In the copper mine in Chile, the hydrothermal fluid going through the rocks and dissolve all those things, and then they bury them on the surface, enrich them on the surface, become the ore deposits. This is, you can think that's a secondary enrichment. Another good example of secondary enrichment is the sulfide piles, or mine tailings. So you have sulfide pile here, sulfide. Those are deposits, okay? And then maybe initially are poor qualities. Okay? Then under the oxide conditions with oxygen, present oxygen, the sulfide, which is sulfur, is reduced sulfur, can be oxidized and turn into sulfuric acid. Sulfuric acids are very low pH. And then they can dissolve all the metals, and then they're going down and going down. At a certain point, and then they could be reduced. When they reduced, and then this turning back to the sulfide. So around board table, then that'll be oxide zone, and then they will be enriched zone. So mineral sulfide will deposit here. So these poor quality sulfide minerals ore, after this process, after secondary enrichment, and then they will turn into ore, which is like 10 or even more, 50 times better, more concentrated in terms of their treatment factor than the original ore deposit. So they become to be secondary enrichment. So on the top, you have iron oxide cap, and then you have this leach zone, which is originally iron sulfide, or copper sulfide. And then they'll be leached, they'll be dissolved, and then when this gets into reduced conditions, they will reprecipitate it. And then you go in here to mine this place and get much better quality ore. Okay. For the sedimentary ones, there are also other minerals from the sea. These are not necessarily sedimentary ones. These are like hydrothermal ones, more like. So one thing is called sulfide deposits. They're massive sulfide deposits contains zinc, copper, iron, trace amount of silver, produced at the black smoker along the ocean ridges. So in the mid-ocean ridges, and because you have volcanoes, right? The volcanoes drives hydraulic cycles. So when at the bottom of the ocean there's water going to ocean crust and then heat up by the volcanoes, and then they're going to come out. And in the process, the water is very hot, and then this dissolving ocean crust. Ocean crust contains mostly the salts, contains a lot of different kind of ions. And then when they come up, and because they're reduced, and in ocean water they have lots of sulfate, and then these sulfates see this reduced liquid, then they will form sulfide. So you'll find zinc, copper, iron sulfide, and they will form this kind of chimneys, and we call that black smokers. And the fascinating thing about black smoker is, first of all, the temperature is very high. Well, for water, it's reached their supercritical point. For seawater, it's about 400 something supercritical point. When going to surface, going to the black smoker is at least up to 350 degrees. So they have very high solubility, and it contains ions. And then when it sees the seawater, which contains sulfate, then they turn making sulfide, making these chimneys. The most fascinating about this is in 1970s, people find that initially people thought that in the bottom of the ocean there's no life. The reason is simple. We know that most of the plants has to conduct photosynthesis. And if in the deep part of the ocean, there's no sunlight, how do they do photosynthesis? If you don't do photosynthesis, there's no plants. There's no plants, then there's no animals. So at the bottom of the ocean, people used to think, in the 70s at least, people think there is no life. But until they have exploration, and they go to the mid-ocean regions, and then they have submarines, small manned and unmanned submarines. They go down there and they find life. They have tube worms, they have crabs, they have all kinds of creatures that live in there and moving around, the little crabs. And then they realize that they are not doing photosynthesis, and they're actually doing chemosynthesis. Chemosynthesis is different from photosynthesis. They actually get the energy from this hydrothermal black smokers. So their heat source, their food, they can use these in doing chemotherapy synthesis and produce their organic matter. Okay, so this is the black smoker. They have iron, copper, iron sulfide. And also, in the bottom ocean, you'll find these kind of things. It's manganese crust or manganese nodules. Okay, so these are the also very important. So you find that in the mid-ocean ridges in Southwest Pacific, flanks of seamount or volcanic ridges, you find this manganese crust. And also you have this manganese oxide nodules, which means that they are like nodules, and they contains manganese, and they have iron, and the second copper, nickel, and cobalt, and so forth. And you find in the Atlantic Ocean of Florida, and then they are in the Central Pacific. They have covered like 20 to 50% of ocean floor, and then they're all on the surface. That's also a mysterious part, and still not a good answer to the question. They're always on the surface. We know that there are sediments deposits on the top, but then they always coming back to the surface. They're always on the surface. So people thought there's a different idea. Some people think that is because when they're buried, it will be reduced environment, they will be dissolved, and they will come to the surface to be oxidized and grow there as well. It's one of the hypotheses. So then similar to that, this is nodule, then there's a crust, which means they're basically forming a crust on the rocks, okay, not completely nodules. Okay, so these are the ways to make deposits, mineral resources. And these mineral resources normally is associated with some kind of plate tectonics. They are mostly at the plate tectonic boundaries, and they have iron, gold, copper, mercury, and so forth. And because the plate tectonic process, especially at the plate boundaries, involve high temperature, high pressure, sometimes partial melting, as we mentioned, that partial melting always accumulating those metals in the melt. High temperature, high pressure conditions will likely the aqueous solution like water can have very high, extremely high solubilities, and they can dissolve them and transport them and enrichment them and along plate boundaries. Or deposit at divergent boundary, normally they are related to migration of ocean water. Basically, it's the black smolter. At the convergent margin, they are related to partial melting of seawater saturated rocks in the ocean lithosphere. And then here, but also in the textbook it's mentioned that they don't oversimplify too much, because it's not all directly related to plate boundary, because sometimes you see this sedimentary and the metamorphism, they are, especially sedimentary, not necessarily be involved, related to the tectonics. In general, consider the subduction in mid-ocean ridges, you have metal oxide and sulfide, black smokers. In the subduction zone, depending on the composition of ocean crust, the melting processes, the angle of the subduction zones, the temperature pressure different, then you have different accumulation of like copper and mercury, and then you have like tungsten in the continent. And again, this is South America, Indies, they have iron zone, then copper, gold, mercury zone. They have lead, zinc, copper zone, and then so forth. So those are actually coming from the subducting slabs, and also the kind of the lithosphere, they accumulating and going up. And depending on the pressure, temperature conditions, the solubility will be different. Therefore, they mobilize different kind of element, and they form this kind of belt. A lot of places you can see that they're related. Those deposits, especially associated with subductions, they are associated with these. They're making some kind of belts. All right. So these are another way to look at that. I mentioned, coming back to that picture showing that most of the big ores, major deposits associated with subductions, mid-ocean ridges has black smokers, and on the floor of the ocean floor you have manganese nodules. The manganese nodules, has people debating whether we need to or how we can mine them, because they have to might be able to disturb the ecosystem, marine ecosystem during the process. So right now it's not mined, but people are thinking about how to mine. And these are the major zones. You can see that in the interior part of the continent where there's no plate tectonics, and you still see bigger, smaller deposits. But bigger ones are also associated with subduction zones, collision zones, and so forth. Okay, so next we're going to talk about socio-economic part of the mineral resources and environment impact. So the environment impact, including during the process of mineral resource, the exploration and application of extraction of mineral resources, over the course of that, there's several steps we can have environment impact. Things like from mineral exploration to testing, to mineral mining, mineral resource refining, mineral waste disposal. They all can have environmental impact. These are depending on many factors like the mining procedures, hydrologic conditions, climate factors, type of rocks and soil, and topography. We're gonna go into one by one. This first, the mineral exploration and testing. Okay, normally people think that this we get information by surface mapping, we get from remote sensing data, and then we have a little geochemical analysis, geophysical, we have little drilling going on there, then test gradings. Then we have an idea of what is the reserves or resource, how much reserve we have in this place. Okay. Normally it's associated with little impact, minimum impact compared to other processes. But you need to have more planning and care for some kind of sensitive areas, especially places like in the textbook said, if you have every place, you have to be aware that in those places normally, in order to protect the soil normally is hiding below the pebbles. You don't want to remove the pebbles. Once you remove pebbles, the soil being blown away, and then it will hurt the ecosystem in the places. And wetlands, same thing. You don't want to kill, animals or for your exploration, porous area as well. So can sometimes some kind of exploration can cause chain reactions. So it's just helpful if you have with certain cautions. Generally have very minimum impact. For the general impact, it can be divided into direct impact and indirect impact. There's direct impact like on land, air, water, biological environment. Indirect impact, including things like environments like a topographic effect, transportation, material, and so forth. And socio environment, like increased demand for housing and service. We're going to go to those things one by one, okay? So the first one is next one is impact from mining operations. So for the mining operation, normally associated with that is the land disturbance from accesses, especially surface mining. Okay, it's more economic. It's much easier. You don't have to drill, but you just put into a truck and then go into the refineries and then you're gonna refine it. But they have very direct environmental effects, and normally surface mining, they have very open pit surface mine, and then in some of these processes, there's a process known as something we call heap leaching is used. For example, like in some places we want to mine gold, they will put cyanide. Okay, we know that cyanide is toxic material. We put cyanide on the rocks, and the cyanide will be able to dissolve a complex with gold, and they're gonna concentrate in some places, and then you collect that in a plastic lined pond, and then treat with covered, and then you recover the gold. And cyanide is very toxic, and the mining process need to be very carefully controlled. And these days, most of those processes has to be banned, because this, where they're reporting that the horses drinking the water and then died, and a lot of things, those things happen. These are called special mining. It's called heat mining from gold mining. So if you imagine that you put all this cyanide solutions on a hill and waiting for those solutions to come down and dripping into a little bucket, and you collect them and extract gold. This sounds pretty crazy, using the poisonous, very extremely poisoned material and try to extract gold and to make a fortune. It's always associated with some kind of hazard. Mining acid drainage, mining acid draining, or during mining, post mining. So this is very similar to the one I mentioned in the secondary enrichment. So this happened a lot in extremes when people try to the mine tailings and the dispose the waste, and then the sulfide, even though it's a low quality, it's not ore, it's some economic. So people don't want to treat them anymore and dump them as mine tailings. And then when they're exposed in oxygen in the air, then they will turn being oxidized, and the sulfide turn into sulfate and sulfuric acid, and they have leachings. Eventually, those will go into, it ends up in streams, so pollute the area where the drainage basin, where the water, streams water can go over, and then cause huge amount of effect. So that's big problems, and kill all the plants, animals along the way, and potentially carry very toxic material, and those can go into the farm, the grains plants, and cause widespread pollution. So these are sometimes it can cause water pollutions. For example, like smelting. When you smelting, basically you burn, you heat up, you melt the ore or rocks, and then during the process you refine that, make it pure. At the same time, you emit all the sulfide returning to SO2. Those are the main compositions of the salt, the acid rings, and it can also affect the biological environment as well. So some examples of water pollution: surface drainage can often alter a mine site, and then runoff from precipitation. They will infiltrate the waste material and leach out the material. So here is one of the examples. Then here basically it's dam prevent all these the liquid, the water, which is being polluted, going downhill. And then some kind of flooding happened, then you see that clearly they're making its way down the slope, and you can see that these kind of waste polluted water everywhere they go through, the vegetation, the plants or trees all die. Okay, so they can have like cadmium, cobalt, copper, zinc, and then when they go down slope. Sometimes also happen is the flooding of these are the zinc mine in Colorado. The white streaks from the name of the mine is called Eagle Mine. They are apparently leached from tailings, and then it contains all those heavy metals and killed all the plants. And these days, these kind of practice in the United States is not allowed today. So this mining stopped in 1979, and then the water quality at the bottom of this river, this Eagle River, actually improved after this mining activity stopped. Okay, so groundwater can also be polluted by this kind of mining exit practice. So another example is this place. This is open pit mine. This is acid drainage mine drainage in Montana, and this is a pit. It's a copper strip mine. Okay, around it, and it's about more than 200 meters deep. And then when the water comes in, and these water are acidic. Okay, so before it closed, all this water actually been pumped outside, and after this mining activity finished, then the pumping stopped. So water is accumulated in those places. The mine was closed in 1982. After several years, water poured here and then formed in this place. It looks pretty nice. It's actually attracting tourists. The question is that the water here is actually very acidic, and also you can't even swim there. It contains harmful trace elements, cadmium, cobalt, copper, lead, aluminum, zinc, and so forth. So these are, it's acidic and toxic. The pH is actually lower than 0, is minus something, so very toxic, and people are finding ways to treat them. It's become a problem. All right. There are also other pollutions. For example, air pollutions. The extraction, processing, operation can have adverse effect on air qualities. Smelting basically releases enormous quantity of pollutant, carbon dioxide, and toxic gas can come from abandoned mines. So pollution can, it can physically or chemically change, have caused physical chemical change in land, soil, and water, and air associated with mining directly, indirectly affect biological environment. A direct impact like death of plants, animals, or people. Indirect impacts like changing nutrient cycles, total mass of all living matter, we call it biomass. We call it reducing species diversity, and it will reduce the ecosystem stability. Right. So in the textbook, there are focuses, and there are some very good examples, a couple of examples. So first one about mining at toxicity. So the first one is the Itai disease is chronic and painful. Itai is actually means ouch, ouch. This is Japanese words, it's tech bones. This disease broke out near the end of World War II, when the Japanese industry complex was damaged, and then the industrial waste disposal practice was largely ignored. The mining for zinc, lead, and cadmium dumped mining waste into the rivers, and farmers used those contaminated water downstream for domestic agricultural purpose. And that rice can concentrate cadmium, so we have high concentration of cadmium in the food. The bones and tissues of the victim of those diseases were actually examined and find constraining large concentration of zinc, lead, and cadmium, and that's big, and a lot of people died. However, it actually takes many years of litigation, to find out what's the reason why there's what's the cause of this disease and why people die. The direct evidence, they take long, tens of years for litigation, and then until those victims, the family of victims get paid in Japan. So it's in Japan, several things happened, about mining toxicity or the chemicals and the toxicities and environmental impact. Another one's mercury as well, and several disease, several pollutions, chemical pollutions happened in Japan, historically caused those kind of environmental impacts, very significant environmental impact. One reason why I control mercury, care about mercury, is because another example happened in Japan, and then there's this disease associated with mercury, and that's the same thing happening. There's not only have this kind of pollution, but also has some kind of litigation, socioeconomic things, and also ethic things, because the company who leaked all those mercury into the environment actually tried to cover up, and then they have litigations. It takes many years to settle down this. And there's a lot of sad stories about this. Now, in the textbook, there's another example of mercury and gold mine. So mercury being used in gold mining since Roman times. It's long history, several thousand years ago. So why mercury? We know that mercury is a liquid state. It's a liquid, and it can move around. And they also very interesting that gold can dissolve in mercury, forming some kind of alloy, and that alloy can move around. So you can easily flow and concentrate gold particles, and then later we can also sort of evaporate the gold, the mercury, and then extract the gold. Make that process very easy. So this is a lot of concerns about mercury, and mercury is a toxic metal. If we get exposure, they can damage brain cells, and they have neurological and nervous system disease, including like fatigue, numbness of arms and legs, and there's lots of problems. So, here are examples. So what people do to get gold is first they do this kind of what's called panning. Is you have a pan, you put sediments in it, and you just shaking and stirring, swirling. And then because the gold has a higher density, like the placer deposit, same thing, then gold actually get the bottom, and then the finer grains of sand, actually when you swirl, they will go out. And then you concentrate gold. At a certain point, you can't concentrate anymore. You see all the black sand and gold together, they probably have similar density. And so it's hard to separate them by panning or doing this kind of saving. Now, what people do is that they put mercury, then the gold will be dissolved. Then you can sort of either filter out this liquid from the solid, which is sand. Then later you can concentrate the gold again. So this process uses a lot of mercury, and after that you might have to evaporate mercury out. Then the gold will be left behind. But the problem is that this is a gold-bearing gravels. A lot of rocks, granite rocks, contains gold. Then gold initially will be 2+, okay, and then these are inorganic gold, mercury. And mercury, at a certain point, they are actually forming mercury methanol mercury, which means that it can have a combine with organic compound. This mercury is very easily being absorbed by organisms, very toxic. And actually, I remember that there was a report when people study this, they actually wear gloves, and then this methanol mercury actually get dropped on the gloves, and they actually can penetrate the gloves and go into skin. And when it's going to skin, that can be absorbed by people. Then the scientist actually died, even though he wear gloves. One layer of gloves is not enough. You have to wear several layers of gloves and special kind of gloves in order to prevent this. So the methanol mercury is very toxic. It's the most toxic form of mercury, and it's very easily can be absorbed by organisms. So, and once you turn this and you go into the creek and river, polluted place, and then cause a huge amount of mercury poison, and then this becomes the problem. An estimate about 4,500 metric tons of mercury was lost into the environment from 1850 to 1880s in California. That's during the gold rush. So people, doing this kind of mining panning, and then they separate them, and then they use this mercury to concentrate them. And these mercury loss into environments is either being water or being evaporated in the atmosphere later with deposit on the surface and go into streams. Okay, so anyway, so these days there are actually regulations since the United States actually produce a lot of mercury and export it to Malaysia, some poor countries which doing this kind of ancient way of gold mining, and then some of them actually, if you don't follow a good practice, they're actually being banned to sell to them. So this is all right. So the social impact. The social impact mostly is caused by the rapid influx of workers in the area of unprepared for growth. So when there's a mine, there's people know there's making monies, then there's a lot of people will come in and take jobs. They need a lot of people. Then they have very huge stress on local services, including water supplies, sewage, and solid waste disposal system, schools, rental housing. That's become a problem. And the land use very quickly shift from open range forest agriculture to urban patterns. Okay. And more people increase the stress on nearby recreation wilderness areas. So people has to entertain. So if it's a fragile ecological balance, construction activities, urbanization affect local streams through sediment pollution, reduce water quality, and increase runoffs. Air quality reduced as a result of more vehicles, dust from constructions, and generation power to run machinery and equipment. Also, there's a reverse social effect when the miners are displaced. If the mine reach its capacity, which means that the mine is decommissioned because either there's too expensive compared, or the good mines already been mined out, and then the mine has to be closed. Then those miners has to be displaced, and then so that, or the mine workers being laid off due to the automation, then that could cause a social impact. So, so how we minimize the impact of mining? So mining potential environmental impacts in development require this. If we want to minimize this impact, we want to have a full knowledge of this process from extraction, refining, product production, waste management. We have to know all of them, and then we can develop strategies how to deal with them and minimize this impact. So also through environmental regulations, we forbid bad mining practices. There's Obama has a Clean Air Act, and also most of the people doing smelting these days has to remove this sulfur dioxide from their gas phase, from their air products, and so that we have less impact on the air. So this clean air production. There's a land reclamation. About 50% of land used in mining industry reclaimed, can be reused after the mine is decommissioned. The important thing is the use of new biotechnology in mining, bio-oxidation, bio-bleaching, bioabsorptions, and also genetic engineering. And we practice the 3 Rs in of the waste management. So one of the another example of a severe environment degradation occurred in Ontario. They are having a century of smelting nickel ores in area produced in the barren land. So you see those chimneys still. There's several chimneys lying here, and these smelting produce sulfur dioxide and forming acid rains. You see they here, being affected. This location the plants just die. This is like a barren land or crop, and they're severely, extensively damaged by air pollutions from the smelters, and then also deposit like mercury, arsenate, cadmium, and to land, water, and biological processes. Okay. So very toxic heavy metals and the emissions of those polluted air, and then and you can see that cause huge environmental damage. Okay, so the biotechnology is something relatively new in mind, and so there's number one is that people find there's bacteria. First of all, it's bacteria. They can do anaerobic activities or aerobic, which means that they can doing oxidation or reducing. So, for example, if I have a acid mine tailings, acid mine drainage, then they are all sulfate, and then if you put bacteria and anaerobic bacteria, then you can turn those sulfate into sulfite. Then the metal will combine with sulfite, turn into sulfite, which is much more stable. So that way you can remove those the pollutions. Or the opposite, you can oxidize some of the materials and make it like cyanide. You can use bacteria to oxidize that, and then they will become dioxide, and then it will become to be less toxic. So there's examples here. Example. So here is the waste, and then they put in the peat, hill valleys, and put here first those biomediation. So they will react it with some of the peat will actually grow, and they have to choose. This is acid mine drainage. Some of the plants here, they can live in acidic water. That is a mushroom compost, provide algae bed, and then so some of the plants can grow, and then through this processes, then the sulfate will turn to sulfite, and then combine with metal, and those water can be cleaned either by turning to sulfite minerals or being absorbed by those plants, and then later we'll treat those plants which solid to so these are sort of the biotechnology. These days, people also use genetic engineering, changing the DNA, their genome of some of the bacteria, so that they can do things that we want them to do. For example, interact with some kind of absorbing or treating some of the metals, combine with some metals, and fix them. Therefore, we can reduce the concentration of heavy metal in those solutions. And sometimes they do using on-site and off-site treatment. We can minimize on-site and off-site problems by controlling sediments, water, air pollution through good energy engineering and conservation practice is the goal. The last, we practice the 3R of waste management. The 3 Rs is reduce the amount of waste produced, reduce, that's R. Reuse material in the waste streams as much as possible, we reuse. Then we recycle, we find a way to recycle them. So this is 3R. Reduce, reuse, and recycle. So recycling mineral resources, why recycle? And the waste from some parts of the mineral cycles may be referred as ore because it still contain material that might be recycled and used again to provide energy or useful products. And some the metals are very toxic to humans. They're dangerous to natural environment. They can degrade, cause the degradation of air, water, and soil. And sometimes when we dispose them, we have to use land for landfills. And so through exploration to resource extraction, they can refine, process, and have metals, products, and disposal coming back to us. This is a sort of cycle. In many places, when we produce the waste, the products can always recycle back to the refining process and going through this small loop. And in this way, we basically, essentially, we can save energy, we can save money, we can save land, we can save raw material resources from ore mining. We can save energy and money when recycling instead refining raw ore materials. And this recycling can prove to be profitable and workable, and because if the waste contains recycled materials. Okay. The most recycled metals like iron and steel, 90% by weight. So the metal, the iron, steel, going back to the refining machines, then coming back the new as good as before. 1/3 as much energy needed to produce steel from recycled scraps as from original ore. So it saved a lot of energy and money. In 2006, the total value of recycled steel in the United States was about $18.5 billion. Recycling iron and steel amount to approximately 50% of those are actually recycled. Lead, about 73%, aluminum, 43%, copper, 32%, nickel, 43%, and titanium, 47%. So these are really profitable. And if you can reduce, you can use the scrap metals to do this, to make a new ones. Okay, minerals and sustainability. Sustainability is defined as long-term strategy for consuming the resources. So normally we thought is that we find alternative material for the metals. Okay. So for example, we use glass fiber cables for copper wires. They have similar properties. And US raw material can use more raw material more efficiently. This is dependent on technology. We saw that the R to C ratio, basically reserve divided by the consumption ratio, that's the time available for finding a solution to the depletion of non-renewable minerals. For example, we see that the evaporite, we have like hundreds of years of time. This is calculated by the known reserve divided by the rate of consumption. That's basically the period of time that give us to find alternative ways, okay, to find alternative materials for these for the mineral resources. Over the course of evolution and mining practice, we find technology, we can use material more efficiently. Then we can increase this R over C ratio. So we have more time for us to find alternatives. Okay. Or we can use this R&D, so this innovative substitute for ways, more research and development on innovative way to substitute or ways to keep this R/C ratio. So if we have find different alternatives, substitutes, then we can increase the R/C ratio. And also, if we have recycles, the 3R practice, we can always also increase this R/C ratio. But thinking about, even though we have like 100 years, what about after a few hundred years? What about we use all of them? And then that becomes the problem. Then we need to find this substitute for most of those mineral resources. All right, that's it. That's the end of chapter 15. And this chapter, we're going to have Answer question, what types of environmental impact would be there if we increasingly extract more mineral resources from seafloor? So this is the question we're going to answer. Okay. All right. So this is also a long chapter. I will expect you to finish this, learning this chapter in a week. Thank you.